Now, an AR model or autoregressive model is just an extension on the random walk, where each term xt is solely dependent on the previous term xt minus 1. So the formula is xt equals xt minus 1 plus epsilon t. And epsilon t is just a stochastic white noise term. Now it's linear because it depends on the previous terms with coefficients for each of those. Now, mathematically, an AR model can be represented like this, or more elegantly, the summation of alpha I plus the term previously with the error term. Now, we need to note that alpha I has to be contained within the real numbers for this to be true. Now, if you consider a backward shift operator or lag operator called b, we can rewrite this as theta p of b xt is equal to 1 minus alpha 1 b minus alpha 2 b squared all the way up to alpha p of b to the p. xt equals the error term. Now you might notice an ARP model is just a random walk with AR1 equal to alpha 1 of 1. Now it's pretty straightforward to make predictions with our ARP model for any time t, because once we have the AI coefficients, our equation can now become x to the t hat equals alpha 1 x to the t minus 1 plus alpha t x to the t minus 2 all the way up to alpha p x to the t minus p. Now, an important thing to notice with this is it's not always stationary, and it depends upon the parameters. To check if this model is stationary, we simply set the characteristics equation, which is this, and set it equal to 0, and solve for b. And we need all the values of the roots to be greater than 1. Now, let's take the random walk for the first example. We're going to let alpha 1 equals 1. So therefore, the characteristic equation is theta 1 minus b. Setting this equal to 0, we get that b equals 1. Now, the value of b needs to be greater than 1 for it to be stationary. So therefore, this is clearly not stationary. Now let's take a look at an AR1 model. So if our AR1 model and our alpha 1 equals, let's say, 1/4, we get that xt equals 1/4 xt minus 1 plus the error term. So then our characteristic equation becomes theta equals 1/4 1 minus b equals 0. Now expanding this out becomes 1/4 minus 1/4 b. Therefore, our b is equal to 4. This is greater than 1, and therefore it is stationary. Now, not all AR1 models are stationary. This is a way to determine if it is or not. Now finally, let's take a look at AR2 models. So let's say that A1 equals A2, which is a half in this example. So we're going to let xt equals a half xt minus 1 plus a half xt minus 2 plus the error term. So our characteristic equation becomes minus a half 1 minus b and then b plus 2, setting this equal to 0. This gives us that b equals 1 and also b equals minus 2. However, since we have a 1, it is not stationary. An important thing to note as well is you need to take the absolute value of the roots. So for example, if we have minus 2 and 3, we take the value, the absolute value, so it gets 2 and 3, and in this case it would be stationary because they both are greater than 1. That's not to say again that AR2 models are non-stationary. This is just this example here. Now the mean of an ARP process is equal to 0, but the autocovariance and the autocorrelation are given by recursive functions known as the Yule-Walker function. I'll leave a link in the description if you want to find out more about them. Next I'm going to show you how to take a time series model and model it in R to see if an ARP model will fit to that description. Now first of all we need a package quant mod, so we're going to do require and then just simply quant mod. If you haven't got that, you can just install it with install.packages and then quant mod. So we need to get the symbols for Amazon, so we're going to do get symbols and then in quotation marks AMZN is the one for Amazon, so we're going to run that. Now to view these, I'm not going to view them all, I'm going to do the top 6. I'm going to do head.amzn and that should print the top 6. Now to save time writing that every time, I'm going to assign x to amzn, just saves me time, and I'm going to plot the closing times of Amazon, which is that command, and then on the right we should see the recent prices of Amazon. Now you'll notice that one thing this is not is stationary, because the mean is clearly not 0, so it increases, and also the variance is a constant. So in order to get it more stationary, we're just going to assign the value y, and we're going to take the difference of this and the logarithmic scale of the closing times of x, which is Amazon. Now to plot this, we'll just do it again. Plot y and check it. Now as you can see, it's centered around 0, so we're getting closer to stationarity. However, the variance is not constant throughout. We're going to create an ACF plot of this. So we're going to do ACF of y, and then we're going to do an dot actions, which basically an dot actions equals dot omit. This basically means of any data set we don't have, we just ignore. Now we notice at k equals 2 there's a significant peak. So there's a reasonable probability of unexplained serial correlation. However, be aware this may be due to sampling bias. So we can fit an AR model and check a confidence interval for all the parameters. To do that, we're going to do y.ar. Now these aren't naming full identifiers, so you can just do Amazon.ar. So we're going to use the call upon the AR function, and we're going to do y, which is our difference returns, and as before we're going to do NA actions, and we're going to take no action, so we're going to omit every value that we don't have. And we're going to run that, and we're going to get the order. So this is going to tell us how many parameters we have. So we're going to do call upon that, and we're going to take the order, and as you can see from the console, we have 16 coefficients of A. So so it goes A to 1, A1 sorry, all the way up to A16. Now to view these, we're just going to do y.ar and AR, and then this displays all 16 values of the coefficients. However, we need to check that these aren't going to be 0, because if we have a coefficient of 0, that makes the xt minus that value also equal to 0, and so the AR16 model becomes less and less and less. So to check this, we do y.ar, and we're going to take the variance of this, which is just asy.far. Now this is created in a sort of matrix style, but we're just going to take the first one. Now what I'm going to do is assign a value of p to the first one, so we can do p equals and then do a matrix of that, so that will give the value of p. So we see that's just that value. So now we're going to create our confidence interval, so we're going to take the first value of AR, which is minus 2. I'm going to copy that into there, and we're going to produce a vector, because we're going to take a 95% confidence interval, which means z equals 1.96. Take a 1.96 from both sides, and we're going to times that by the square root of p. Now, as you can see, 0 is contained within the first A1, so therefore it could be 0, the whole coefficient. We'll do the second one now, just to demonstrate that they're not all 0. So if we get this value, plug that into there, and again we're going to take the value of 1.96, it's 1.9, sorry, it's a 95% confidence interval, so square root of p, and we get that we've got minus 0.0859 and the upper bound of minus 0.01. So 0 isn't contained within that, so we can be 95% sure that A2 hasn't got 0 contained, so therefore we can be confident of that value. However, if you just take all these coefficients, it will be less than 16 as demonstrated in the first one. Therefore we know that an AR model would not fit Amazon.